in order for it to be its own transpose, of course, it better be square, right? Because if you start with an m by n matrix, if it's m rows and n columns, what will its transpose be?
N by m.
N by m, and if it doesn't have the same size, it can't be equal to itself, right? Okay. So symmetric definitely requires it to be square. And we're going to require square for the diagonal and the triangular. So let's just write these down real quick for definitions. So just for the symmetric, a matrix A is symmetric if it's its own transpose. So notice that that requires it to be square, right? If it's going to be, to have any hope of equaling its own transpose, it's going to have to be a square matrix, right? Now, in the books, usually in books, it goes in and says square in here. Square, it's requiring it to be square ahead of time is kind of superfluous. This is going to require it to be square if that's going to be true, just by a size argument. All right, for triangular matrices, actually diagonal is a special case of a triangular matrix. So as far as triangular matrices go, you can kind of imagine what they have to look like. And we talked, I think I mentioned this a couple of days ago, maybe a couple of class periods ago. But for a matrix to be triangular, you look at the diagonal. If it's going to be upper triangular, then there's zeros below it. If it's going to be lower triangular, it's going to be zeros above it. And then for it to be a diagonal, it's zeros both above and below it. Okay. So just to write that down, a square matrix, let's do diagonal first. A square matrix A is diagonal if it's zeros everywhere except for the diagonal. So writing that in terms of the entries. Now notice that you can be a diagonal matrix and still have a zero on the diagonal. This just says that whenever we're not on the diagonal, so whenever I is not equal to j, then the entry has to be 0. Okay? So, for example, if you had something like 1, 0, 0, 3, that's a diagonal matrix. But this would also be a diagonal matrix. I'm okay with the 0 being here, right? Whenever we're not on the diagonal, I have to have zeros everywhere else. That makes sense? Now, let's look at these two examples in particular and think about it in terms of invertibility. This is something we're going to come back to in the next chapter with determinants and invertibility. And these matrices happen to be easy to do in terms of determinants. But just let's think about it in terms of invertibility. If I want to do the inverse of this matrix, let's think about what happens when you multiply by this matrix. Well, if I take this 1, 0, and I think I mentioned this the other day, if I take this 1, 0, 0, 3 and multiply it by any other matrix, notice that if you do it quickly, this entry here gets multiplied across the first row, right? So this entry that's in the 1, 1 corner gets multiplied completely across the first row, and we don't add anything to it because there's going to be zeros everywhere else in that row, right? When we take this entry, and we multiply by this row, this entry gets multiplied by the second row, and nothing else happens, right? Because there's zeros everywhere else. So notice the effect of multiplying by this entry, this matrix, multiplies the first row by this entry, multiplies the second row by this entry. And that would happen in general. right? This is the way it's going to match up when we multiply. So, thinking about it that way, what would be the inverse of this matrix? How can we do the inverse of this matrix pretty quickly without having to go through a row reduction idea? What does the inverse have to be? So again, this has the effect of multiplying a matrix by 1 by the first row and by 3 by the second row. So we need to undo that.
1, 0, 0, 1 third.
Good. 1, 0, 0, and 1 third. We just need to reciprocate the diagonal. Undoing this, multiplying the second row by 3, we need to multiply the second row by a third. Does that make?
And that's because you're getting it back to the...
Because we're trying to, when we multiply these two things together, we get back to the identity.
Okay.
So undoing that 3 requires multiplying it by a third.
So it's like what we just did with like the two separate ones and getting it like
Yeah.
to the same thing.
Yep. All right, so let's look at the second matrix there that I put as an example. Do you think that one's going to be invertible? No. What's wrong with it? There's a 0 up there, right? And if no, try as I might, I'm never going to get that to be a 1. If we try to think about a row reduction, right? But also think about what that does. If I multiply this on the right, excuse me, if I take a matrix on the right here and multiply, what's it going to turn the first row into? Zeros, right? We've talked about that before, right? If I take a matrix of the row of zeros and multiply it on the left of another matrix, it's going to make a row of zeros in the same spot. That's why we can never have an inverse. We can't have an inverse for a matrix that has a row of zeros, because I can't multiply it by something and get back to the identity. Because as soon as I multiply it by something, I get a row of zeros, right? The same thing happens to be true for columns, right? If I have a column full of zeros, if I multiply it if it's on the right of something, you'll end up with a column in the same space, the same place that has zeros in it. So matrix with a row of zeros can't have an inverse. A matrix with a column of zeros, matrix with a row of zeros can't have an inverse. A matrix with a column of zeros also can't have an inverse. Okay. But again, notice that when we do the inverse of a diagonal matrix, if we think about it this particular way, I have to be able to do the inverse, essentially, of each of the diagonal entries, or do the reciprocal of each of the diagonal entries, which we can't do here because of that 0 in the upper left-hand corner. Nothing special about it being in the left-hand corner, it just happens to be where I wrote it. Does that make sense? Okay. All right. So let's talk about the other types of triangular matrices. The square matrix A is upper triangular if, well, think about the picture, and then I'll write down what the definition has to be. No, this is not that's not an example, this is a definition, sorry. Example's down here. Sorry about that. Let's think about what the picture, what the example is, and then we finish off the definition. All right, so say I made that as my matrix. So I've got 3, 2, 0, 0, 1, 5, 0, 0, negative 7. So that's upper triangular because if I think about making the triangle, that was a weird way to emphasize that word. Think about making the triangle here. That's where the non-zero entries are. That's why it's upper triangular. The potential non-zero entries are the diagonal and anything above the diagonal, up and to the right. That's upper triangular. Okay. So from this example, let's think about what we need to write down in terms of the entries. So here, what would be the subscripts for this entry right here? How would we describe the subscripts here for this entry?
1, 2, 2, 1.
2, 1, right? Because it's row 2, column 1. Always you row first, then column. This one is
3,
3, 1, and 3, 2. So all the ones that we know have to be 0. What's true about the subscripts? Which one's bigger? The row subscript or the column subscript? The row subscript is bigger, right? So if we go back up to the definition, then A sub, I don't want this in red, then A sub ij is 0 whenever the I subscript is bigger than the j subscript. The row subscript is bigger than the column subscript. Row number bigger than column number. Does that make sense? That was why I went with the example first and then wrote with the definition. So you could really see an actual honest to goodness example of why the definition is the way it is. How's the definition going to change for lower triangular, do you think? Yeah, it's the exact same definition except that you're going to flip the inequality for the I and the j, right? So again, if we think about the example first, if we think about lower triangular, again, I think about where the triangle is. Here's the triangle that we're talking about for lower triangular. The only possibilities for the non-zero entries are on the diagonal or below it, down and to the left. So think about the subscripts that are here above the diagonal. This entry, what's the subscript be here?
1, 2.
1, 2. This one would be 1, 3, and 2, 3. So the row number really is smaller than the column number, right? So if we do the definition for lower triangular, oops, I forgot the word matrix in my previous definition. I just noticed that. It's the same definition written over again, except that I'm going to flip the inequality there at the end. So same idea. Yes?
So in the first example, something in the triangle, like it can be 0.
It can be 0, yeah. The only thing we're requiring is that anything below the diagonal has to be 0.
Okay.
Yeah. So, in particular, if you have a diagonal matrix, it's both upper and lower triangular. Because there's zeros above and zeros below. So diagonal ones are both upper and lower. And the 0 matrix would be all 3 as well, even though that looks really weird. But the 0 matrix is diagonal and upper triangular and lower triangular. Just the way the definition works. So is the identity matrix. Because when we're saying these definitions for the triangular matrices, we're not worried about what the entries are actually in the triangle. We're worried about what the entries are for the ones that aren't in the triangle. Okay. Now, one of the things that is nice, well, there's several things that are nice about triangular matrices, which is why they're studied. One of the things that are nice is the way they multiply together. So let's just do a quick example and then see what we think the theorem might be. If I multiply the matrix, let's say 1, 3, 2, 0, 2, 1, 0, 0, negative 1, and multiply it by 2, 1, 0, 0, negative 2, 3, 0, 0, 4, say. Just go ahead and do the multiplication. All right, so when I take the first row times the first column, we just get 2. Right? And then if I take the first row times the second column, we get 1 minus 6, so we get negative 5. And if I take the first row and the third column, we get, what, 9 plus 8, so 17? I'm doing my arithmetic right? All right, so that's not the interesting part, because I still had to do some computations. Notice I didn't have to do as many computations as I would have otherwise. Well, I know these two entries are 0. The only real the entry that I need to multiply is the 1 and the 2, right? The other ones I know are going to be 0. So it actually saves some computations if I have these upper triangular. But notice what happens when we do the next entry. When I take this row and match it with this column, what happens? What do we get?
0.
We get 0, right? We're going to end up with a 0 in that same spot. The next two entries are going to be what? -4, and then 6 plus 4 is 10. I did my arithmetic right. So again, the last two there aren't as interesting. Now what happens in the third row? When I match row 3 and column 1, what do I get? 0. When I take row 3 and column 2, what do I get? 0 as well. And then I get -4. So notice when I took the product of these two upper triangular matrices, it stays upper triangular. I don't introduce new non-zero entries here when I take the product of the two. The same thing happens for lower triangular matrices. So the theorem is the product of two upper, respectively, lower, or diagonal. I should put the word triangular in here before I write that diagonal part. Matrices is upper triangular, and then again respectively lower triangular and diagonal. And this is just mathematicians being lazy again. It's shorthand for saying when a mathematician writes respectively, it's basically the mathematician is saying write the exact same sentence again, just replace with the next word in the parentheses. Write the same sentence again, but replace with the next word in the parentheses. So products of upper triangular is upper triangular. Product of lower triangulars is lower triangular. Product of diagonals is diagonal. It's just shorthand for that. Like I said, part of the goal of this class is to do some introduction to proof. To do introduction to proof, you got to do introduction to reading math. And this is one of the things that pops up in reading math. So the respectively part just means I'm too lazy to write 3 sentences. I want to write 1. So I'm just going to do a substitution for the words. And then what you'll actually see a lot is that they'll actually abbreviate respectively as RESP. ECT, yeah, I know what it means to me. All right, so let's do a proof of this. I think one of these is in your review idea. They do the proof of lower triangular in the book. I think upper triangular is on the review, if I remember correctly. So let's do diagonal just to give you a third one. I know that diagonal is not on the review. So I think upper diagonal is on or upper triangular is on the review. Lower triangular proof is on page 70 in your book under theorem 1.7.1. Okay. So for the proof here is let's let A and B be diagonal matrices. And we want to show that the product of the two is diagonal. So what does that tell us about the, before I write down what the product has to look like, what does that tell us about the entries for A and B? Okay, so certainly the matrices are square, right? What do we know about the individual entries? Or at least most, I'll say most of the individual entries. What do we know about most of the individual entries?
That when I is not equal to j.
Good. So then we know that A sub ij is 0, and so is B sub ij when I is not equal to j, right? We know that for a fact, correct? So if I want to show that their product is 0, I need to show that the product has the same property, right? Whenever I is not equal to j, then I need to get a 0, correct? What does a general entry, what does a general entry look like for the product? Just what does the entry look like? How do we write a general entry for a product of two matrices? So sum, good. I didn't give, bless you. I didn't give these, I did put in the subscripts what the dimensions were. But if they're square, what do we usually use for square? N by n, right? So what does my sum run through? Yeah, but it'll be 1 to n, right? And what do we match up? Rows to columns, right? So what do I write first?
A sub aj
I k, yep, and then b sub kj, right? So think about it this way. We need to run through the ith row of the first one as we run down the jth column, right? If I'm going to run through the ith row, I can't change the row number. Right? If I'm going to run down the jth column, I can't change the column number. So that's what this needs to look like as far as a general entry. Now again, if you're going to write this out, this looks like A sub I1, B sub 1j, A sub I2, B sub 2j, all the way out to A sub IN, B sub nj. Right? Because the k is what changes. All right, so we want to show that the product is diagonal. So again, what's the defining characteristic? What's the specialness of being a diagonal matrix? What has to be true?
That all entries that are on diagonal are 0.
Okay, so all entries not on the diagonal are 0. In terms of the subscripts, how do we specify that an entry is not on the diagonal? Good. So whenever I does not equal to j, we need to show that this c sub ij is 0, right? All right, so let's see if we can do this. Oops. All right, so I left a gap in the middle here, and let's talk about why I left a gap in my plus. All I did was, instead of writing it out with the summation, I wrote it out longhand here, right? Okay. I left a gap in the middle. Let's think about why I left a gap in the middle. What do we know about A and B? What do we know about the matrices A and B?
Square.
What else do we know? Okay, and they're also the same size, and what else do we know?
They're diagonal.
They're diagonal, right? Okay? Lots of things we know. Diagonal is the one that I needed for this one. All right. So since they're diagonal, what do I know about the A's here? What do I know about the A's in particular? Okay, they're 0 except for which one?
AII.
Yeah, they're all 0 except for AII, right? Somewhere between 1 and n, we hit I, correct? So that's why I left this gap in the middle. Somewhere in between, there's an A sub II, B sub ij. No matter what I and j are, somewhere in the middle between 1 and n, I have to hit A sub ii, correct? Now again, you just told me, Ryan just told me, that this entry is what? And this one is, and this one is 0. The only one I don't know that's 0 is that one, correct? I don't know whether or not it's 0. Could be. Could also be pi, it could be e, it could be cube root of 96, right? There's lots of different things it could be. I don't know what it is. But I know the rest of those that I underlined are definitely 0. So this is 0 times b sub 1j, 0 times b sub 2j. I don't know what a sub ii is, but then I get 0 times b sub nj. So I still left a gap here. I know all the rest of them are 0 though, correct? Without a doubt. All right. I still don't know that c sub I, right now, at this stage, I still don't know that c sub ij is 0. And that's what we want to prove. But what are we assuming about I and j? Well, so the relationship between I and j, what are we assuming? Are I and j the same? No. You say whenever I is not equal to j, correct? Okay, so what do we know about the b's now? Yeah, they're all 0s except for bjj, correct? Is this bjj? No. This is bij, right? So what do we know about this entry then?
0.
It has to be 0, yeah. So this one is 0. So what does the whole entry have to be then? 0. Good. So now we can conclude that C is diagonal, or that the product is diagonal. Because we showed that when we're not on the main diagonal, the entry has to be 0. So the matrix is diagonal. By the way, this is exactly how you prove product of upper triangulars is upper triangular, product of lower triangulars is lower triangular. You still write out the terms like this, and you find the switching point. You do the a sub ii and find where it switches. Okay. So in the case where it is lower triangular, remember, if the row number is bigger than the column number, then it's 0. That's lower triangular, right? Row number bigger than column number, it's lower triangular. You still switch here. At this point, all of the row numbers get to be bigger than the column numbers for the A's, right? So all of those will be 0. At this point, up until that point, all of the row numbers for B will be bigger than the J. Or did I do that backward? Might have done that backward. Up until this point, all of the row numbers are bigger than the column number for A. I didn't do it backward. So all of these will be 0, and then at this point it'll switch. So because you'll start by assuming that whenever I is greater than J, we have. You'll do the same kind of thing. So if you do lower or upper, it's the same proof. You do it the same way, you just have to switch it a little bit. But the idea of the proof is exactly the same. So like I said, the proof for lower triangular is in your book on page 70. And I think I did upper triangular is on the review sheet. I think that's the right one that's on there. But you can see that literally the 3 proofs are the same. Except that this has changed. And then you have to just figure out which ones are 0 as you're writing out the sum. But again, that II term is where it's going to switch. Because that's when you hit the diagonal for the matrix A. So that's why you call it out, especially in the sum. Right. One of the reasons, again, why I wanted to do this was to give you a way to prove that, or just a way to, another example of proving things with entries. Now, unless I ask you to, don't try to prove things by going to the entries. Okay? So, for example, one of the things that we talked about was symmetric. If you're asked to show something symmetric, don't go to the entries, right? Okay? You had one on your homework with symmetric and skew symmetric, I think it was, but using the properties of how the transpose distributes is helpful. So, for example, let's say we have, let's suppose that A is symmetric. Yeah. I think the one you had in your homework was the following. That was the one you had in your homework, I think. So to prove something is symmetric, you have to show that it's its own transpose. So I want to start with A transpose A, take its transpose, and where do I want to end up? The same thing back again, right? To show something is symmetric, I want to start with the matrix that I have, take its transpose, and get back to where I started. Actually, I don't think I even needed the fact that A is symmetric here. I think I get this as symmetric for free, but that's okay. Doesn't matter. All right. Actually, I don't want. Let's ignore that part, the first part. I don't really want this part, because otherwise it's not a very interesting proof. Let's just show that A transpose A is symmetric no matter what. So I want to show that it's its own transpose. That's just in general. So the first thing I notice is I have a transpose of a product. How do we do transpose of a product? You distribute it, and then what do you do with the factors? Reverse them, right? So this is A transpose, and then A transpose, transpose, right? Remember, you have to do them in the reverse order, correct? AB transpose, AB quantity transpose is B transpose, A transpose. Okay. Now what happens when you transpose a matrix and then transpose it back? You get the original matrix back, which is exactly what we have over here, don't we? So that is the whole proof that it's symmetric. That would be it. All right. So the property, just to remind us of the property that we used, was the fact that if I do the transpose of a product, it's the product of the transposes, but in the reverse order. What other property was similar to that? Inverse, right? If I do the inverse of a product, it's the product of the inverses in the reverse order. Now, of course, this works no matter what. A and B can be any size that you want as long as you can multiply them, right? But what has to be true here before I can even start talking about these? Say it again?
The same size.
Yeah, they better be the same size because why? Well, we're multiplying them so I can make sure the columns and the rows match, but also I have to be able to do the inverse of each one, so they better be what kind of matrix. Before I can even talk about inverses, what kind of matrix do we have to start with? Square, right? So they better be able to be square. And they better both be invertible. We'll talk about this. Okay? So the first one here works as long as you can multiply A and B. It's the only restriction. They don't even have to be square, right? As long as they can be multiplied, this is true. Okay? However, over here, the individual matrices have to be invertible. So they have to be square plus, you have to be able to take their inverses before you can do that one. All right. basically just trying to remind you of some properties, trying to do a little bit of review as we go along here. So let's do some more ideas of review. So things that, of course, you'll be expected to do. You'll need to be able to do row reduction, put things in reduced row echelon form, reduced row echelon form, either or. Right? But where we started was solving systems of equations. So part of that involves row reduction, but after you row reduce, you got to be able to write down the solutions, right? So if you had something where I had a matrix, say, and I wrote down, let's say, 1, 0, 3, -2, 4. And let's put a 0 here just for argument's sake, and then a 0 here. Let's say 0, 1, -2, 0, 5, 0, and then 0, 0, 0, 1, 3, 0, and then a row of zeros. Let's say you ended up here after your row reduce. First, since I have zeros on the right-hand side of that vertical bar, what kind of system did we start with? If we have all zeros on the right-hand side of your equality, what kind of system is that called? Starts with an H. Starts with an H and lots of syllables.
Hedonistic.
Hedonistic? I don't think so.
Homogeneous?
Yeah, homogeneous is what we say in math. But yeah. It's a homogeneous system. Okay, so when you have all zeros, that means it's a homogeneous system. Okay. Homogeneous systems can homogeneous systems ever be inconsistent?
No.
No, because what always works? All zeros for your variables, right? So homogeneous systems are always consistent. They always have at least one solution, no matter what. Okay? In this particular problem, how many free variables do you see? 2. I see a free variable here and here, right? So if I say that's x3 and x5, say, what do we use for those? Yeah, usually just use parameters, right? S and T. So then I need to write the other ones in terms of those parameters. So what will x4 be? Good, -3t. What will x2 be? Good. And what will x1 be? Good. Right, remember the vertical bar is representing the equal sign, correct? So all you need to do is, now think about it, if you think about equations, you're just moving this over to the other side, right? So x4 would be -3t. x2 is 2s minus 5t. It just flips the signs around. Right? Because go ahead, Megan.
So the whole row, like, I don't know what I'm trying to ask. So, like, each row has the same variable?
Right, because remember, these are representing the coefficients for the x1, x2, x3, x4, x5.
Yeah.
Right. So if our x3 here is s and x5 is t, then I would move those to the other side to solve for the x1. Right, because this equation refers to x1 plus 3x3 plus 4x5 equals 0. And I want to solve that for x1 in terms of the other ones. Okay. If we write this as in vector form, we've got an S and we've got a T. What has coefficients of S's, or what has S's in it, I should say? Yeah, the x1, the x2, and x3, right? So, all right, -3, 2, 1, and then 0, 0 here. And then what has coefficients with the T? All but 3. So we have -4, -5, 0, -3, 1. So being able to row reduce it to this point, this is in reduced row echelon form. Being able to row reduce it to that point is important, but also being able to write down what the solutions are is important, right? So that was what we did in the first couple of sections, just writing systems of equations, solving them, those kinds of things. The third section had your matrix operations in it, so defining addition, subtraction, multiplication. All those things were in section 3. And then section 4, I think it was, that actually started talking about the properties of arithmetic, the different rules for arithmetic. That was section 1.4. And that was really when we were starting to use the general entry of a matrix to prove a property. So looking at, say, theorem 1.4.1 had all the different properties. And then there's a proof of one of them on page 40, which talks about distribution. Being able to prove those types of properties would be something that would be fair game. We also defined inverse in that section. And then on section 5 is when we went to how we found the inverse of a matrix through row reduction, and then talked about elementary matrices. So just to reiterate again, 1.4 introduced the idea of inverse, and a few of the properties, like if you do an inverse of a matrix and then do the inverse again, what do you end up at? The original, right? Or if you do the inverse of a product, is the product of the inverses in the reverse order. And the ways we prove those things were the fact that we use the property that inverses are unique, right? The reason that A inverse is A is because it acts like the inverse of A inverse. A acts like the inverse of A inverse. The reason that A inverse transpose is A transpose inverse is because A inverse transpose acts like the inverse of A transpose, right? It's all of that, all of those types of proofs that we did in that section have to do with the fact that inverses are unique, right? It's an important property that inverses of a matrix are unique if it exists, okay? Like I said, section 5 talked about elementary matrices and how you can do row operations with elementary matrices, how you can write a matrix as a product of elementary matrices. All of those were in section 5. Section 6 was when we did that nice big theorem. I talked about different conditions that mean the same thing as invertibility. And we also did a couple of things in section 6 that had to do with consistency, right? You had a system of linear equations. They put some b's on the right-hand side and said, row reduce and see what has to happen with the b's to make it consistent, right? Notice that they put some b's on the right-hand side and did that. You could have put some numbers on the right-hand side and put some letters on some coefficients. I mean, say you had an AX1 and then said, what does A have to be in order to make it consistent? could have done that way too, right? But there was nothing special about putting b's on the right-hand side. There could be variables, there could be conditions on constants on the left-hand side. Okay? But you do it the same way. You would stick it in a matrix, row reduce it, and see what has to happen. Okay? If you had something that looked like, say, maybe you're going along, you've got I don't know why, but maybe you got this as your row reduction. Okay? If this, say you're at, this is always consistent because, again, what kind of system have I written down?
Homogeneous.
Homogeneous system? Hurts my ears. Homogeneous system here, right? Okay? So we already know it's consistent. It already has one solution. What if you wanted infinitely many solutions? You wanted non-trivial solutions, right? The trivial solution, all zeros, is always a solution, right? But what if you wanted non-trivial solutions? What would have to be true? If you wanted non-trivial solutions, what would have to be true?
We have to get a pivot in a second.
Do you want to pivot or don't want to pivot?
You do.
If I get a pivot, then I get that equals 0, right?
You don't want to.
Yeah, I don't want to pivot, right? If I want infinitely many solutions, I don't want to pivot, correct? So what's going to have to be true to get infinitely many solutions here?
B equals -2/3.
Yeah, the b better be -2/3, right? Because I need a 0 there, correct? If I'm going to get infinitely many solutions, this entry right here has to be 0 to get infinitely many solutions, to get non-trivial solutions. One of the things that we're going to be interested in later this semester is exactly that. What conditions do we need to get non-trivial solutions? Pops up to be an important concept later on. So, as far as the test goes, your first question will be true-false. There'll be 10 true-false questions. Okay. That's always, pretty much, that's always the first question of the test of mine in advanced classes. There's a true-false thing. Okay? Advanced proof classes, I should say. Then there'll be some computational stuff, right? Do you know how to do row reduction? Do you know how to write down solutions? Do you know how to do a matrix operations? Right? There'll be some computational things. And then there'll be some conceptual things. Can you do a proof with using general elements? Can you do a proof with doing properties? Right? Do you understand some of the results of being, how do I make something consistent? How do I make something with infinitely many solutions? Those kinds of things. Okay. Again, I'll be here at 8 for you to start at 8. In here, I already have a room reserved. We have 8 to 10. I know a few of you have an 8 o'clock class, so if you need to schedule a different time to do it, make sure you have a nice 2-hour block to do it in. Just let me know. Yes.
Would you say that it will most likely take the full 2 hours, or is it more just a safety precaution to make sure we have enough time?
I would say most people probably take over an hour, but it's more of a safety precaution that you'll get done in 2. Yeah. That's the idea. All right. Have a good one. We'll see you Friday.